Humanity's most distant emissary, Voyager 1, is more than 15 billion miles away, and we know its location down to the inch. This is the pinnacle of navigation. But this achievement is a deadly illusion in the depths of space, because that information reaches us with a delay of almost 2 days. In real time, we are completely blind, as Earth orbits the Sun at 67,000 miles per hour, while our entire system travels through the galaxy at over 500,000 miles an hour. Your map home quietly becomes wrong. But that's not the most frightening part. The most frightening part is that even time itself begins to shatter. If you want to delve into the depths of this cosmic riddle, a riddle that even the smartest engineers cannot solve, like and subscribe. Because in a moment, you will see why the journey home is not an engineering problem, but an impossibility of physics. Here we go. For years, we thought the universe was a fixed stage. We believed the stars were unchanging lights, hung in the sky. Our home, Earth, was a safe, stable point at the center of this cosmic theater. But this was just an illusion. Then we started to look farther and deeper, and we understood the fundamental nature of the universe. Nothing stands still. Nothing. We know now that the place you call home is not a location, but a moment, and that moment is lost forever the instant you turn your back. To understand this truth, we must descend to the first concept at the core of everything. Home is a moving target. What does this mean? Simply put, as you read these words right now, the planet is spinning on its axis at over 1,000 miles per hour at the equator. That may seem slow to you, but that's just the beginning. The same planet is hurtling through its orbit around the Sun at approximately 67,000 miles per hour. That's better, but it's still not the whole picture. Because the entire solar system, with the Sun and all the planets, is orbiting the center of the Milky Way galaxy at an incredible speed of roughly 500,000 miles per hour. And the Milky Way itself is not stationary. Our galaxy is being pulled toward a massive structure we call the Great Attractor at over 1 million miles per hour. When you put all these movements together, you realize that Earth is not in the same place 1 second as it was the second before, ever. So why does this matter? Because it shows that in the depths of space, there is no such thing as going back. There is no place to return to. There is only the struggle to predict the future position of a target that has traveled billions of miles during your journey and to reach it. But why don't we feel this motion? When you wake up in the morning, your house is right where you left it yesterday. This reveals the second fundamental concept, the illusion of a shared reference frame. Everything on Earth moves together. You, your house, the Earth's crust, the atmosphere, all move in the same direction at the same speed as part of a single system. This is similar to not feeling the motion when you're on a train. The seat next to you, the window, the other passengers are motionless relative to you, because you're all inside the same system. But the moment you look out the window, you see how fast the landscape is rushing by, and leaving for deep space is like jumping off that train. In an instant, you're separated from everything you were moving with. The moment you leave Earth, compasses, maps, even your phone that gets a signal from a satellite, become meaningless, because they're all based on fixed points on the Earth's surface, or predictable satellites in Earth's orbit. But even that isn't the real problem. The truly interesting part is just how massive this shared motion is. In just 1 day, Earth travels over 1.6 million miles in its orbit, and in 1 year, the entire solar system travels over 4 billion miles within the galaxy. Why is this critical? Because when you try to find your way in deep space, your instincts betray you. Your sense of direction is shaped by a stable ground. But in space, there is no ground, and every tool you might use to find your home was designed for this stable ground that no longer exists. In this situation, an obvious solution comes to mind, right? Using the stars, just as ancient mariners did. This is the third and most deceptive concept. the false security of celestial navigation. Close to Earth, this method works wonderfully. Stars appear almost completely fixed on the scale of a human lifetime. Their real motion, what we call proper motion, is so slow that it's unnoticeable for decades, even centuries. This is why NASA's spacecraft like Voyager and New Horizons were able to find their way even billions of miles away. The cameras on the spacecraft photograph the positions of bright, just well-catalogued stars. A software compares these positions with the map in its memory. By measuring the angular shifts between the spacecraft, the stars, and known objects like the Sun, Mission Control can calculate the vehicle's position with incredible precision, sometimes with an error margin of just a few miles. Voyager 1 is currently 15 billion miles away from us, and we know its exact location. This relies on the assumption that the stars form a fixed background. But that very assumption is the biggest lie that makes a deep space journey impossible. This trick has a limit, and the moment you cross that limit, every single point of light in the sky begins to betray you. And this is where the problem becomes layered. Your home is a target in constant motion, never in the same place twice. All the navigation tools you use on Earth become instantly useless because they rely on the illusion of a shared motion. And your last hope, the stars, which seem to be the most reliable guides in the universe, are actually part of a secret deception. Their stability is just a game of perspective. So what happens when all these local rules collapse and the universe itself refuses to guide you? How can you find your way in a void of trillions of miles when even the most reliable map in your hand is slowly turning into a lie? Because when you try to find your way across a void of trillions of miles, the universe itself begins to use two new and powerful weapons against you. These are laws of physics you don't even notice at close range, but which turn into monsters as you approach the speed of light. This is why the stars betray you. Two separate problems emerge at the same time. The first of these is stellar aberration. What does this mean? It's like the rain hitting your face at an angle when you're running. Even though it's actually falling straight down, your movement makes the direction of the raindrops seem to change. The same thing happens with light. When you reach a significant fraction of the speed of light, the position of every single star in the sky begins to shift. The faster you go, the more dramatic this shift becomes. The stars start to bunch up in front of you, in the direction of your travel, and spread out behind you. The entire sky literally bends. Every reference point your navigation system relies on appears in a different place than your maps say it should. But that's not the most dangerous part. The most dangerous part is that the amount of this shift is constantly changing along with your speed. When you accelerate, your map is wrong in one way. When you decelerate, it's wrong in another. Why does this matter? Because it proves that there can be no universal map. Your map is a temporary document, specific only to your instantaneous velocity, and that document becomes invalid the moment you change your speed. It's like trying to find your way with a map that is constantly being redrawn. But that was just the first problem. The second, and more insidious issue, is proper motion. Remember how we said stars appear fixed on the scale of a human lifetime? That was true for short missions. But when your journey lasts for decades, or even centuries, that assumption collapses, because stars really do move. They orbit within the galaxy on their own paths, and this slow drift becomes noticeable over a long journey. The stars you use to set your course at the beginning of your voyage will have moved by the time you reach the end. Some a little, others much more, depending on their distance and true speed. The command to head for the second star to the right, like in Star Trek, becomes meaningless. Because by the time you get there, that second star may no longer be there. Why is this critical? Because it fundamentally destroys the greatest assurance in navigation, the idea of a fixed reference point. Imagine the lighthouses you trust are constantly moving. It would be impossible to reach a harbour using them. That is precisely the situation in deep space. All these problems lead us to one painful truth: the collapse of distance perception. We measure the distance to nearby stars using the parallax method. If you hold your thumb in front of your face and look at it first with one eye closed, then the other, you see your thumb jump against the background. That's parallax. Astronomers do the same thing by looking at the same star from two different points in Earth's orbit, and they calculate the star's distance from the amount of that jump. This method works great for stars within a few thousand light years. But the baseline we use for measurement, the width of Earth's orbit, is comically small compared to interstellar distances. The farther a star is, the smaller the parallax shift becomes. And after a certain point, the shift becomes so tiny that it's no longer measurable. The star appears fixed, no matter what its true distance is. Now imagine yourself in that spacecraft. You're no longer measuring from Earth's orbit, but from a constantly changing reference point, at a speed close to the speed of light. Every point you thought was stable becomes uncertain. Every star you use to check your position shifts, both because it's actually moving and because your own motion distorts your perception of it. This is the deepest irony of deep space navigation. The very tools that keep us safe when we are closest to home, the stars, become our greatest enemies when we venture farthest away. We understand that home is a moving target. The reference points on Earth are an illusion of shared motion, and the stars become unreliable due to both our speed and their own movement. So, when all these traditional methods failed, what did the engineers do? They didn't give up. They searched for a natural mechanism in the universe itself, a clockwork that could bring order to this chaos, and they found it. But this solution would bring its own set of impossibilities. It's time to put theories aside and look at the real technologies developed to solve this cosmic riddle and their surprising limits. And now we come to the truly shocking findings, because theories and concepts only go so far. But real data can make you forget everything you thought you knew. Engineers decided to use signals coming from the universe itself to solve this cosmic navigation problem, and this quest led them to the most unexpected, most powerful, and most dangerous solutions. The first solution was to correct one deception with another: radio signals. This seemed like a perfect idea at first. NASA's Deep Space Network consists of massive antennas spread across California, Spain, and Australia. The system is simple. You send a signal from Earth, wait for the spacecraft to send it back, and measure how long that round trip takes. Since the speed of light is a constant and known figure, 186,000 miles per second, engineers can calculate the distance from this time with extraordinary precision. They can also find its speed by measuring the signal's Doppler shift. That is, how its frequency changes if the spacecraft is moving toward or away from us. When you combine distance and speed, you get a perfect picture of where the vehicle is. We know exactly where Voyager 1 is, 15 billion miles away, using this very method. But this method has a fatal weakness. It is dependent on Earth. Because the speed of light is painfully slow compared to the scale of the universe. It takes about 8 minutes for a radio signal to reach the distance of the Sun. To reach Voyager 1, it takes more than 23 hours. So when you send a message, you wait almost 2 days just to get a reply. Now extend this journey to decades. The communication time is no longer measured in hours, but in years. You ask a question, and by the time the answer arrives, the situation you asked about no longer exists. The spacecraft has moved. The advice from mission control is already obsolete by the time it reaches you. This method does not guide you. It only gives you a slow history lesson about where you were years ago. It is completely useless for real-time navigation. So, what's left when communication with Earth is cut off? The second and most obvious solution, dead reckoning. The art of navigating by yourself. The same thing ancient mariners did for centuries. You carefully record your speed, your direction, and how long you've been traveling. Then you calculate your position from this data. For a few weeks of ocean travel, this works. But this method also has a fatal weakness. Errors accumulate. Every small error you make in measuring your speed, every tiny deviation in your course, every unaccounted force acting on you, adds to the previous one. On a journey of a few weeks, this error might be a few miles, annoying but correctable. But now extend this journey to decades and trillions of miles. The uneven impact of the solar wind on different parts of your spacecraft, the slight gravitational effects of distant passing stars, the never-perfect inefficiencies of your thrusters micrometeoroid impacts too small to be noticed, but which shift your course by 1,000th of a degree. None of these are significant on their own. But dead reckoning cannot correct an error it doesn't know about. Over interstellar distances, a constant error of just a fraction of a degree would cause you to miss your destination by a distance greater than the width of an entire star system at the end of a 4 light-year journey. You wouldn't just miss your target, you wouldn't even realize you passed it. That's why dead reckoning alone is suicide. It needs to be constantly corrected by external references, but we've already seen that the stars are also unreliable. And now we come to the most brilliant, most promising, and perhaps most ironic solution: pulsar navigation. Pulsars are the collapsed cores of massive stars that have exploded as supernovae. They spin at incredible speeds, some hundreds of times per second, and as they spin, they sweep beams of radiation through space like a lighthouse, some of them known as millisecond pulsars. Tick, with an unfailing regularity, with a precision that rivals the best atomic clocks we have on Earth. The idea is elegant. If you can detect the timing of the pulses from several pulsars scattered across the galaxy, and you know their exact positions and periods, you can calculate your own 3-dimensional position. This is similar to how GPS works, but instead of satellites, you use collapsed stars spread across thousands of light years. NASA tested a version of this concept on the International Space Station. A device detected the X-ray pulses from several known pulsars and calculated the station's position using only these signals, and it worked. The position calculated by pulsar timing matched the station's known orbit with an error margin of a few miles. This was a remarkable achievement. But this method is not a perfect solution either, because the X-ray signals from distant pulsars are incredibly faint. To detect them clearly, you need large, sensitive instruments and long observation times. A fast-moving spacecraft that needs constant position updates cannot afford the luxury of sitting for hours listening for faint signals from specific stars. Moreover, even pulsars are not eternally constant. They slow down. As they radiate energy, they slow down over time. So while they may be stable for decades, they are not perfect over centuries and millennia. Here, the pieces of the puzzle come together. Communication with Earth collapses due to the slowness of the speed of light. Self-navigation becomes impossible due to accumulated errors, and even the most precise clocks in the universe, pulsars, have both practical difficulties and long-term instabilities. Every solution seems to breed a new problem. So, beyond all these instruments and calculations, could there be another problem etched into the very fabric of space-time that deepens the issue even further? Yes, there is. Because, beyond all these instruments and calculations, the problem that deepens the issue is etched into the fabric of space-time itself. And this problem targets your most personal or most fundamental perception. Time. I present to you time dilation, one of the strangest and most proven predictions of Einstein's theory of relativity. What does this mean? The faster you move, the slower time flows for you. Not for you, of course. The clock on your ship still appears to tick normally. But, to someone on Earth, your clock has slowed down at everyday speeds, in cars and planes. This effect is so small it's meaningless. But when you reach a significant fraction of the speed of light, it becomes dramatic. Travel at 90% of the speed of light. For every 1 year you spend on the ship, more than 2 years pass on Earth. Go up to 99% of the speed of light. This ratio increases even more. For a single year you experience roughly 7 years pass on Earth. Why does this matter? Because it reveals a disturbing truth. Even if you perfectly solved all the navigation problems, even if you knew exactly where you were and how to steer your ship to the solar system, the place you returned to would not be the place you left, depending on how long your journey took and how fast you went. Decades, or even centuries, may have passed on Earth by the time you get back. The people you knew would be gone. The cities you remembered would be unrecognizable, or may no longer exist. Home doesn't just become a difficult place to find. It no longer exists. At least, not as you left it. But that is only the beginning. There is another hidden layer that makes navigating the universe impossible. the collapse of human perception. In the depths of space, there is no up or down. There is no nearby horizon, no landscape against which you can measure your motion. Even the astronauts on the International Space Station, despite being weightless, have a planet to look at, a sunrise and sunset every 90 minutes, and constant contact with mission control only a fraction of a second away. But in deep space, none of this exists. To a human, the stars all seem to be at the same infinite distance. Whether it's 4 light years away or 40,000, it makes no difference. Without instruments, a person drifting in deep space has no way of knowing which direction they're going, how fast they're going, or even if they are moving at all. This is not just unsettling. This kind of disorientation has been proven to be one of the most psychologically taxing aspects of space travel. All the ordinary cues your brain relies on for navigation disappear. Why does this matter? Because it shows why deep space navigation can never be based on instincts or observation. Every single piece of position information must come from instruments, from calculations, from models, and all of it is filtered through imperfect data, corrected with imperfect assumptions, and is never entirely certain. And now we go to the very deepest level. To the philosophical and physical truth at the heart of all these problems, the absence of a fixed point. In the late 1800s, scientists believed the universe was filled with an invisible medium called the ether, a fixed background against which all motion could be measured. If this medium existed, you could theoretically measure your velocity against it. It would be the ultimate reference point of the universe. 2 scientists tried to detect it with an incredibly sensitive instrument. They aimed to measure tiny differences in the speed of light, based on Earth's motion through this supposed ether. The experiment was precise, repeated many times, and the result was the same every time. Nothing. Zero difference. Light travelled at the exact same speed no matter which direction it was measured in, no matter how Earth was moving. This result baffled physicists for years, until a new explanation came along. There was no such thing as ether. There was no fixed background. There was no universal frame of reference against which absolute motion could be measured. Motion was only meaningful, relative to something else. Why is this critical? Because this is the deepest reason why finding the way back home is so difficult. The problem is not just that our instruments aren't good enough. The problem is that the universe itself is not built with an absolute frame of reference. Every position, every velocity, every direction only has meaning relative to something else, and everything else is also moving. As you can see, the problem deepens layer by layer. Time itself bends and leaves you in the past. Human perception loses all the cues it relies on, and at the most fundamental level, the universe itself offers you no fixed branch to hold on to. So in this seemingly impossible equation, can modern technology offer us a way out? Can the logic behind the GPS in our pockets be scaled up to an interstellar level? So, in this equation that seems so obviously impossible, can modern technology offer us a way out? Can the logic behind the GPS in our pockets be scaled up to an interstellar level? Let's get technical now, because the answer to this question is yes and no. GPS, the Global Positioning System, works so flawlessly that we don't even think about how it works. But the logic behind it is a perfect starting point for understanding why deep space is so ruthless. Now we will peel back the layers of that flawless system, one by one. Let's take a closer look at how the GPS system works. It is a network of clocks orbiting the Earth. Imagine a constellation of satellites orbiting at an altitude of about 12,000 miles. Each satellite carries an atomic clock so precise it would lose less than a second in roughly 3 million years. This is incredible precision. Each satellite constantly broadcasts its exact position and the exact time that signal was sent. Your phone or your car receives signals from several of these satellites at the same time, and it measures the tiny differences between the arrival times of these signals. It then calculates its own position through a process called trilateration. This is essentially triangulating yourself against several fixed and known points in the sky. Just like standing in a room and knowing your exact location. By knowing your distance to 3 different pictures on the wall, it is an elegant system. And the reason it works is because it meets a set of conditions that deep space does not offer. The satellites are close. Their positions are known with extreme precision at every moment. Enough satellites are visible from any point on the Earth's surface to allow for accurate triangulation. And most importantly, the entire system operates within a communication delay measured in milliseconds, not hours or years. None of these conditions exist the moment you leave the solar system. There is no network of precisely known satellites surrounding you. There is no dense cluster of calibrated reference points broadcasting their position within fractions of a second. The stars that could play a similar role are light years away. Their signals take years to update, and as we've seen, the faster and farther you go, the more their apparent positions shift. GPS is a marvel of a closed and controlled system. Deep space is an open, uncontrolled, and chaotic system. So can't we just build a GPS-like network? That idea has been considered too. You can imagine humanity deploying a network of navigation beacons into nearby interstellar space. Artificial satellites broadcasting known positions like GPS satellites. But building and maintaining such a network across light years would be a colossal undertaking in itself. Keeping each beacon precisely calibrated for centuries and receiving their signals with a usable speed and accuracy is far beyond what current technology can realistically achieve. For the foreseeable future, deep space travelers will have to rely on the universe's own imperfect beacons and hope that those beacons are enough. This brings us to another fundamental tool, a tool that is easy to overlook but has been with us for thousands of years: magnetism, Earth's magnetic field. Generated deep within our planet's molten outer core, this field extends far beyond the surface, creating a protective bubble called the magnetosphere. It protects us from much of the sun's radiation, and it has been used for navigation for thousands of years, since the invention of the first compass. But Earth's magnetic field, no matter how useful, only extends so far. Beyond it lies a much larger bubble carved out by the solar wind, the heliosphere, a continuous stream of charged particles flowing outward from the sun. The heliosphere extends to about 11 billion miles from the sun, far beyond the orbit of Pluto. It acts as a kind of border between our solar system and true interstellar space. In 2012, Voyager 1 became the first human-made object to cross this boundary, leaving the heliosphere and entering interstellar space directly. When a spacecraft crosses this boundary, every trace of the familiar, locally generated magnetic structure disappears. There is no compass to rely on, even in principle. The interstellar magnetic field out there is weak, complex, and shaped by forces completely unrelated to our sun or solar system. It offers nothing similar to the reliable, well-mapped magnetic field that has guided sailors and pilots on Earth for centuries. Any spacecraft or future traveler passing into that region loses yet another tool that worked reliably closer to home. In that case, without external references, shouldn't we turn to completely self-contained systems? Yes, and that brings us to the purest form of navigation: inertial measurement units. These systems are instruments that directly measure their own motion without needing to look outside. They use gyroscopes and accelerometers to detect changes in orientation and velocity. In principle, if you know your exact starting position and can measure every single acceleration and turn the spacecraft experiences afterward, you should be able to calculate your current position entirely by internal measurement. This is the pure form of dead reckoning. It has been successfully used to guide missiles, submarines, and early spacecraft with impressive accuracy for relatively short periods. The Apollo missions relied heavily on inertial navigation, with gyroscopes tracking the spacecraft's orientation throughout the journey to the moon. But even those systems required regular correction with star sightings. Because gyroscopes drift. Tiny imperfections in their construction, small amounts of friction, slight sensitivities to temperature changes, cause small errors to creep in over time. These errors accumulate just as dead reckoning errors accumulate at sea. For a 3-day trip to the moon, this drift was manageable. It was periodically corrected with precise star sightings made with an onboard telescope. But for a journey of decades and trillions of miles, the same drift would be catastrophic. Even the most advanced modern gyroscopes, while precise to a small fraction of a degree per hour, would accumulate enough error over years of continuous operation to throw a spacecraft's calculated position off by an unacceptably large amount. There is currently no gyroscope, accelerometer, or inertial system made by humans that can maintain a useful accuracy over the timescale required for a true interstellar journey, at least not without frequent correction from some kind of external reference. And we have already seen how difficult, how delayed, and how uncertain those external references become. We understand that our most precise local system, GPS, is useless in space. Our planet's natural compass, the magnetic field, disappears after a certain distance, and even our most advanced internal navigation systems fall victim to their own errors over time. Each technological solution seems to hit a wall against the immense scale of the universe. But what if the problem isn't with the instruments, but with the very thing we are looking at? What if light itself, our most reliable source of information, starts to play games with us as we accelerate? Yes, it does. Because when you reach a meaningful fraction of the speed of light, light itself stops being a carrier of information and becomes a collection of deceptions. This is a subtle distortion that deeply affects navigation, and it has to do with color. When an object moves toward you, the light it emits shifts toward the blue end of the spectrum. This is called blue shift. When an object moves away, its light shifts to red, which is called red shift. This effect is extremely useful for measuring the motion of distant galaxies. But for someone traveling at a significant fraction of the speed of light, it becomes a major complication. At these speeds, the stars in front of you appear blue shifted, sometimes dramatically. The stars behind you are red shifted, and the degree of this shift is constantly changing as your own speed changes. What does this mean? A star that would normally appear as a familiar reddish or yellowish point of light might instead appear bright blue. Its true color is completely masked by your own velocity relative to it. Identifying stars by their expected color, one of the ways astronomers use to recognize and catalog specific stars from great distances, becomes unreliable right when you need it most. In the most critical phases of a long journey, at the highest speeds, every visual identification method you rely on is corrupted by the very fact of moving fast enough to make the journey survivable in a human lifetime. Just as a piece of music becomes unrecognizable when played too fast, the universe's color palette changes with your speed. This means your map starts to misrepresent not just the positions, but also the identities of objects. What about the environment? Does this entire journey take place in a perfect void? No. And that brings us to another silent enemy, the interstellar medium itself. Interstellar space is not a perfect vacuum. It contains a sparse but real amount of gas and dust. It is also filled with a constant bombardment of cosmic radiation, high-energy particles that have been racing through the galaxy for millions of years. Some originate from ancient supernova explosions. Exposure to this radiation over years and decades can degrade sensitive electronics. It can slowly shift the calibration of the very instruments a spacecraft relies on to measure its position and orientation. A star tracker that was precise to a fraction of an arcsecond when it was launched might lose its calibration slightly after years of radiation exposure, and it could then introduce small, hard-to-detect errors into every position calculation it makes thereafter. Dust particles, although incredibly sparse in interstellar space, still occasionally impact the surface of a spacecraft at a significant fraction of the speed of light. Even a microscopic particle carries enough energy to cause real damage, or at the very least, an unpredictable small jolt to the spacecraft's trajectory. None of these effects are dramatic on their own. But navigation over interstellar distances is not broken by a single dramatic failure. It is slowly eroded by dozens of small, easily overlooked factors, each adding a little more uncertainty to a picture that was never perfect to begin with. And finally, we come to the invisible force behind all this motion: gravity. Every star a spacecraft passes near, even from a distance of light years, exerts a small gravitational pull on its trajectory. Most of the time, this effect is negligible. It is too small to matter for practical purposes. But on a journey of decades and trillions of miles, even negligible effects accumulate. They subtly divert an orbit from its initially calculated path in ways that are hard to predict in advance. Because These effects depend on the precise mass and position of every star along the way, and many of these are not known with perfect accuracy from observations made from Earth. Astronomers have catalogued the positions and estimated masses of a great many stars. But small errors in those catalogues, when multiplied by the length of an interstellar journey, add another layer of uncertainty to any attempt at precise long-term navigation. It is like sailing on an ocean filled with invisible and unpredictable currents. No matter how well you chart your course, there will always be imperceptible forces slowly pulling you off track. We understand that light, our most fundamental source of information, deceives us by changing color as we accelerate. The environment we travel through slowly blinds our instruments with radiation and dust, and the universe itself constantly bends our path with invisible gravitational strings. Every system, every mechanism carries a flaw within it. But that's not the most exciting part. The most exciting part is how, despite all these impossibilities, humanity has developed incredibly clever, almost poetic methods to solve this problem. Now, we will witness the most dramatic moments, the greatest victories, and the most heartbreaking failures in the struggle to find order in the midst of this chaos. And now comes the real miracle, because we're about to see how, despite all these impossibilities, humanity has developed incredibly clever, almost poetic methods to solve this problem. Here are the greatest tests and the brightest solutions. These are the most dramatic moments in the struggle to find order in the midst of chaos. We are reaching the climax now. Get ready. Because technology and human ingenuity are challenging the universe itself. The first epic moment was the Apollo 13 crisis. This is one of humanity's greatest triumphs in space, but it is also the most terrifying proof of how fragile deep space navigation is. The mission was on its way to land on the moon. But an oxygen tank exploded about 200,000 miles from Earth. The spacecraft was crippled. The lunar landing was cancelled. The only goal was survival. The only goal was to get home. The primary navigation computers were partially shut down to save power. The crew and mission control had to find a way to verify the spacecraft's orientation, and they did. What they used was incredible: the sun. They simply aligned the sun, visible through a window, with a specific mark against known star positions. Simple, primitive. But it worked. But what was behind this success? Extraordinary precision, cool-headedness, and most importantly, a massive ground team that could communicate with the crew in seconds, run calculations on powerful computers, and send instructions back almost instantly. Earth was clearly visible in their windows as a steadily growing blue marble. Communication delays were only a few seconds, and the margin for error was razor thin. Now imagine that crisis, but not 200,000 miles away, 200,000 times farther away, in the true interstellar void. No growing blue marble in the window, no quick radio chat with mission control, and no way to visually confirm your orientation against anything known. The tools that saved Apollo 13, a visible Earth, a visible sun, instant radio contact, simply would not exist in deep space. It was humanity's greatest rescue operation. But it was also the most bitter lesson in why such a rescue would be impossible in deep space. But that was just a beginning. There was something bigger. Humanity wanted to leave a permanent mark on the universe, a message. I present to you the Voyager Golden Records. This is one of the most poetic gestures in human history. When Voyager 1 and Voyager 2 were launched, each carried a golden record designed as a message to any civilization that might one day find it drifting in interstellar space. Etched onto the cover of that record is a map, but not an ordinary map. A map showing the position of our sun relative to 14 specific pulsars. Each pulsar is identified by its precise rotation period at the moment of launch. It was coded in a way that would allow a technologically advanced civilization to calculate exactly where and roughly when the spacecraft came from. This is essentially a cosmic return address, built using the same pulsar timing principles that modern engineers are now trying to turn into a practical navigation system. The fact that scientists in the 1970s chose pulsars out of everything in the universe to mark our location says something important. Even then, they understood that ordinary reference points, ordinary coordinates, would mean nothing over such vast distances and timescales. They needed something that would still be meaningful tens of thousands of years later, something durable enough to survive the drift of every closer, more familiar reference point. Pulsars were the closest thing to a fixed address in an addressless universe. But even that address comes with a significant warning. Because pulsars slow down as they age, the exact timing encoded on that record will slowly become less accurate the farther into the future it is read. This means that even humanity's carefully designed cosmic return address has a kind of expiration date, a slow drift toward inaccuracy, built into the physics of the very stars it relies on. Even our most permanent message cannot escape the ever-changing nature of the universe. And now we come to the most incredible thing, an idea that bypasses this entire problem. Because if you don't have to come home, you don't have to find the way. I present to you one-way settlement missions, some mission concepts, like generation ships or other extremely long-duration journeys, are not designed around the idea of ever returning. They are designed to transport people to a new home, rather than attempting the much more complex, much more risky return journey. This approach, in a strange way, circumvents almost everything we have discussed tonight. Not by solving the navigational challenge of finding the way back, but by eliminating the need to ever try. There would still be immense difficulties in accurately reaching a chosen destination on the first try. All the challenges of dead reckoning, star tracking, and long-term instrument drift still apply to the outbound journey. But at least there would not be a second, even more uncertain calculation for a return trip. There would be no attempt to re-find a home that has moved even farther away over decades or centuries of being apart from it. This is a pragmatic, if somewhat sobering way of acknowledging just how difficult the return half is. Sometimes the most realistic answer to a nearly impossible challenge is not a clever new technology. It is choosing not to attempt the hardest part of the journey at all. It may be humanity's ultimate adventure, but it is also a one-way trip. It is setting out knowing you can never go home again. And now we scale up to the grander scale, mapping the universe itself, because if there are no reliable reference points, then we must create them. I present to you the Gaia Space Telescope, launched by the European Space Agency. Gaia has spent years precisely measuring the positions, distances, and motions of nearly 2 billion stars in our galaxy. It has produced the most accurate map of the night sky ever created. It is this map that makes modern star tracking possible, and each new release of Gaia's data has steadily improved the precision of spacecraft navigation systems. Must it? But even a map this detailed and carefully measured is, by necessity, a snapshot, a single frozen moment in a constantly changing sky. Every star in that catalogue continues to move after the measurement was made, and the catalogue itself needs to be periodically updated to remain useful, especially for missions expected to operate long into the future. For a mission lasting a few years, this is not a major concern. But for a hypothetical mission lasting decades or centuries, even the best star catalogue ever produced must be treated not as a permanent, unchanging truth, but as a starting point. It is another piece of the layered, imperfect system that deep space navigation ultimately relies on. Gaia drew the best map of the universe, but even that map begins to age the moment the ink is dry. The universe itself moves faster than we can map it. As you can see, every solution, every heroic effort confronts a deeper truth of the universe. Apollo 13 showed how critical, but how short-ranged Earth's help is. The Golden Record proved that even our most permanent address fades with time. Generation ships proposed escaping the problem by accepting the impossibility of return, and Gaia revealed that even our best map is temporary. So, what is the ultimate, most staggering truth that lies at the heart of this problem, a problem that remains unsolved despite all these monumental efforts? Because the ultimate, most staggering truth that lies at the heart of this problem is this: the problem is not just that we don't know our location. The problem is that the universe itself does not recognize a concept of now in the way we understand it. This is one of the most difficult ideas for the human mind to grasp, and it transforms deep space navigation from an engineering problem into a philosophy problem. Now, we come to the biggest and weirdest discovery: the death of the present moment. This idea goes against our most basic intuitions. We think we know what now means, but that is just a local assumption. Because Information, including light, can only travel at a finite speed. This is why two observers moving at different speeds or separated by great distances do not have to agree on what is happening at the same time. This is not a measurement error. This is a fundamental feature of how space and time are woven together. For someone traveling in deep interstellar space at a significant fraction of the speed of light, the concept of Earth's current position becomes slippery in a way that has nothing to do with measurement error and everything to do with the structure of reality. When now ceases to mean the same thing for every observer, there is no single, universally agreed upon answer to the question, where is Earth right now? It is not that the map is wrong, it is that the very concept of a map collapses. Because Beras, a map shows positions at a specific moment in time, but if that moment is not the same for everyone, for whom is the map correct? This shows that navigation is not just an engineering problem, but a riddle woven into the fundamental physics of the universe. The same physics that seem to promise us a fixed cosmic reference frame, instead reveal that no such thing has ever existed. No matter how well you chart your course, there will always be imperceptible forces slowly pulling you off track. We understand that light, our most fundamental source of information, deceives us by changing color as we accelerate. The environment we travel through slowly blinds our instruments with radiation and dust, and the universe itself constantly bends our path with invisible gravitational strings. Every system, every mechanism carries a flaw within it. But that's not the most exciting part. The most exciting part is how, despite all these impossibilities, humanity has developed incredibly clever, almost poetic methods to solve this problem. Now, we will witness the most dramatic moments, the greatest victories, and the most heartbreaking failures in the struggle to find order in the midst of this chaos. And now comes the real miracle, because we're about to see how, despite all these impossibilities, humanity has developed incredibly clever, almost poetic methods to solve this problem. Here are the greatest tests and the brightest solutions. These are the most dramatic moments in the struggle to find order in the midst of chaos. We are reaching the climax now. Get ready. Because technology and human ingenuity are challenging the universe itself. The first epic moment was the Apollo 13 crisis. This is one of humanity's greatest triumphs in space, but it is also the most terrifying proof of how fragile deep space navigation is. The mission was on its way to land on the moon. But an oxygen tank exploded about 200,000 miles from Earth. The spacecraft was crippled. The lunar landing was cancelled. The only goal was survival. The only goal was to get home. The primary navigation computers were partially shut down to save power. The crew and mission control had to find a way to verify the spacecraft's orientation, and they did. What they used was incredible. The sun. They simply aligned the sun, visible through a window, with a specific mark against known star positions. Simple, primitive. But it worked. But what was behind this success? Extraordinary precision, cool-headedness, and most importantly, a massive ground team that could communicate with the crew in seconds, run calculations on powerful computers, and send instructions back almost instantly. Earth was clearly visible in their windows as a steadily growing blue marble. Communication delays were only a few seconds, and the margin for error was razor thin. Now imagine that crisis, but not 200,000 miles away, 200,000 times farther away, in the true interstellar void. No growing blue marble in the window, no quick radio chat with mission control, and no way to visually confirm your orientation against anything known. The tools that saved Apollo 13, a visible Earth, a visible sun, instant radio contact, simply would not exist in deep space. It was humanity's greatest rescue operation. But it was also the most bitter lesson in why such a rescue would be impossible in deep space. But that was just a beginning. There was something bigger. Humanity wanted to leave a permanent mark on the universe, a message. I present to you the Voyager Golden Records. This is one of the most poetic gestures in human history. When Voyager 1 and Voyager 2 were launched, each carried a golden record designed as a message to any civilization that might one day find it drifting in interstellar space. Etched onto the cover of that record is a map. But not an ordinary map. A map showing the position of our Sun relative to 14 specific pulsars. Each pulsar is identified by its precise rotation period at the moment of launch. It was coded in a way that would allow a technologically advanced civilization to calculate exactly where and roughly when the spacecraft came from. This is essentially a cosmic return address, built using the same pulsar timing principles that modern engineers are now trying to turn into a practical navigation system. The fact that scientists in the 1970s chose pulsars out of everything in the universe to mark our location says something important. Even then, they understood that ordinary reference points, ordinary coordinates, would mean nothing over such vast distances and timescales. They needed something that would still be meaningful tens of thousands of years later. Something durable enough to survive the drift of every closer, more familiar reference point. Pulsars were the closest thing to a fixed address in an addressless universe. But even that address comes with a significant warning. Because pulsars slow down as they age, the exact timing encoded on that record will slowly become less accurate the farther into the future it is read. This means that even humanity's carefully designed cosmic return address has a kind of expiration date, a slow drift toward inaccuracy, built into the physics of the very stars it relies on. Even our most permanent message cannot escape the ever-changing nature of the universe. And now we come to the most incredible thing, an idea that bypasses this entire problem. Because if you don't have to come home, you don't have to find the way. I present to you one-way settlement missions, some mission concepts, like generation ships or other extremely long-duration journeys, are not designed around the idea of ever returning. They are designed to transport people to a new home, rather than attempting the much more complex, much more risky return journey. This approach, in a strange way, circumvents almost everything we have discussed tonight. Not by solving the navigational challenge of finding the way back, but by eliminating the need to ever try. There would still be immense difficulties in accurately reaching a chosen destination on the first try. All the challenges of dead reckoning, star tracking, and long-term instrument drift still apply to the outbound journey. But at least there would not be a second, even more uncertain calculation for a return trip. There would be no attempt to re-find a home that has moved even farther away over decades or centuries of being apart from it. This is a pragmatic, if somewhat sobering way of acknowledging just how difficult the return half is. Sometimes the most realistic answer to a nearly impossible challenge is not a clever new technology. It is choosing not to attempt the hardest part of the journey at all. It may be humanity's ultimate adventure, but it is also a one-way trip. It is setting out knowing you can never go home again. And now we scale up to the grandest scale, mapping the universe itself, because if there are no reliable reference points, then we must create them. I present to you the Gaia Space Telescope, launched by the European Space Agency. Gaia has spent years precisely measuring the positions, distances, and motions of nearly 2 billion stars in our galaxy. It has produced the most accurate map of the night sky ever created. It is this map that makes modern star tracking possible, and each new release of Gaia's data has steadily improved the precision of spacecraft navigation systems. Must it? But even a map this detailed and carefully measured is, by necessity, a snapshot, a single frozen moment in a constantly changing sky. Every star in that catalogue continues to move after the measurement was made, and the catalogue itself needs to be periodically updated to remain useful, especially for missions expected to operate long into the future. For a mission lasting a few years, this is not a major concern. But for a hypothetical mission lasting decades or centuries, even the best star catalogue ever produced must be treated not as a permanent, unchanging truth, but as a starting point. It is another piece of the layered, imperfect system that deep space navigation ultimately relies on. Gaia drew the best map of the universe, but even that map begins to age the moment the ink is dry. The universe itself moves faster than we can map it. As you can see, every solution, every heroic effort confronts a deeper truth of the universe. Apollo 13 showed how critical, but how short-ranged Earth's help is. The Golden Record proved that even our most permanent address fades with time. Generation ships proposed escaping the problem by accepting the impossibility of return, and Gaia revealed that even our best map is temporary. So, what is the ultimate, most staggering truth that lies at the heart of this problem, a problem that remains unsolved despite all these monumental efforts, because the ultimate, most staggering truth that lies at the heart of this problem is this. The problem is not just that we don't know our location. The problem is that the universe itself does not recognize a concept of now in the way we understand it. This is one of the most difficult ideas for the human mind to grasp, and it transforms deep space navigation from an engineering problem into a philosophy problem. Now, we come to the biggest and weirdest discovery, the death of the present moment. This idea goes against our most basic intuitions. We think we know what now means, but that is just a local assumption, because information, including light, can only travel at a finite speed. This is why two observers moving at different speeds or separated by great distances do not have to agree on what is happening at the same time. This is not a measurement error. This is a fundamental feature of how space and time are woven together. For someone traveling in deep interstellar space at a significant fraction of the speed of light, the concept of Earth's current position becomes slippery in a way that has nothing to do with measurement error and everything to do with the structure of reality. When now ceases to mean the same thing for every observer, there is no single, universally agreed upon answer to the question, where is Earth right now? It is not that the map is wrong, it is that the very concept of a map collapses. Because Beras, a map shows positions at a specific moment in time, but if that moment is not the same for everyone, for whom is the map correct? This shows that navigation is not just an engineering problem, but a riddle woven into the fundamental physics of the universe. The same physics that seem to promise us a fixed cosmic reference frame, instead reveal that no such thing has ever existed. But let's make a jump from this philosophical impasse to a practical solution. I present to you very long baseline interferometry. This is a technique engineers use to determine a spacecraft's position with even greater precision than simple round-trip timing. This shows just how clever our current methods are, and how fundamentally they are tied to Earth. Instead of relying on just one antenna, engineers use 2 or 3 widely spaced dish antennas, sometimes on different continents. They receive the same signal from a distant spacecraft at very slightly different times, because it takes the signal a little longer to reach one antenna than the other. Engineers measure this tiny timing difference with extreme precision, and they compare it to the known, fixed distance between the antennas themselves. This allows them to calculate the spacecraft's direction in the sky with much better accuracy than a single antenna could achieve alone. Combined with the distance measurement obtained from simple round-trip radio timing, this gives mission control an extremely precise 3-dimensional fix on a spacecraft's true position. It is one of the reasons we can track something as small and distant as Voyager 1 with such confidence. But notice once again what this method fundamentally relies on. It relies on multiple, fixed antennas on Earth, precisely measured, precisely synchronized, working together as a single giant instrument. Move the spacecraft far enough away, and extend the communication delay from hours to years. This technique, like all other Earth-based methods, becomes useless for real-time navigation, and this brings us to the heart of the entire system. The thing that makes everything possible, but also limits everything. Fuel. Every correction to a spacecraft's trajectory, no matter how small, requires firing thrusters, and every thruster firing consumes fuel, a resource that can never be replaced once a mission has left Earth. Mission planners have to balance accuracy with conservation, correcting the course often enough to stay on target, but not so often as to deplete the limited fuel supply long before the journey is complete. For missions within the solar system, this balance is manageable. It has been refined by decades of practical experience. But for a journey over interstellar distances lasting years or decades, this balance becomes far more delicate. Every correction burns fuel that a returning traveler might desperately need later, especially if unexpected deviations, unexpected gravitational tugs, or unexpected instrument errors require larger, more urgent corrections at the end of a journey that is already running low on fuel. In principle, you could carry more fuel to allow for more corrections, but in practice, more fuel means more mass, and more mass means requiring even more fuel just to accelerate that extra weight. A self-reinforcing trade-off that engineers call the tyranny of the rocket equation, one of the most stubborn, inescapable constraints in all of spaceflight. This shows that navigation is not just an information problem, but also a brutal resource management problem. No matter how clever you are, when your tank runs empty, the game is over. When we bring all these technical and physical obstacles together, the picture becomes clear. The concept of now itself ceases to be a universal reality. Our most precise Earth-based tracking system becomes useless at long distances, and every single maneuver is paid for with an irreversible price: fuel. All these walls, all these limits, force us to one thought. Maybe the problem is not figuring out how to get home. Maybe the real problem is redefining what we call home. But now, before we dive into these philosophical depths, it's time to stop and think. What do all these technical challenges, these physical impossibilities, mean for the human spirit, for our species? But now, it's time to stop and think. Because, what do all these technical challenges, these physical impossibilities, mean for the human spirit, for our species? All this data, all these equations, cause us to ask one of the most fundamental questions. What exactly is our place in this vast, indifferent universe? We are moving away from speed, shock, and discovery, and now entering the calm waters of meaning. Because, sometimes, the greatest discoveries are not made out there, but in here. Let's confront the first and most obvious contrast, the contrast of scale and meaning. On one hand, there is a scale that pushes the limits of the mind. 4 light years, the distance to the nearest star, is roughly 25 trillion miles. This is such a large number that it has no meaning. It is impossible to feel it. We know that a small navigational error of 1 degree results in a deviation of more than 400 billion miles at this distance. This means an error margin wider than our entire solar system. We are smaller than a grain of sand in this universe. Our movements are meaningless against the rotation of the galaxy. Our lifespan is but a blink of an eye compared to the lifespan of stars. This is a tragic truth. On the vast stage of the universe, we are physically insignificant. Even our greatest ships, our fastest rockets, are no different from a plankton in this cosmic ocean. And the most painful part is realizing how fragile, how lonely that little blue dot we call home is in this infinite darkness. But here comes the but moment, because being physically small does not mean we are semantically small. Yes, we can never walk a distance of 25 trillion miles, but we can calculate that distance, we can understand it, we can make that journey in our minds. Knowing that a 1 degree error will cause a 400 billion mile deviation is a more powerful act than making that error. This is the triumph of consciousness. The universe itself may be large, but it is not aware of its own largeness. We, however, are aware. And this awareness elevates us from being passive inhabitants of the universe to its active observers, its understanders. You are part of this paradox. Your body may be tied to this planet, but your mind can travel to the 2 billion stars mapped by Gaia. It can feel the danger faced by Apollo 13. You can understand the hope carried by Voyager. You are the answer to a question the vast, silent universe asks itself. Now let's move to a second contrast. The contrast of loneliness and connection. Deep space is the definition of absolute loneliness. There is no up or down there. There is no horizon. There are no reference points. A human is drifting there without instruments cannot even feel if they are moving or not. This is a feeling that researchers have studied in people isolated for months in Antarctica or in submarines. The loss of time perception, a strange sense of detachment. Suski. But deep space offers something that even these experiences do not: an absolute, singular loneliness. Even the closest man-made object to you, your spacecraft, hangs alone in a void of trillions of miles. This is one of the hardest tests the human spirit can endure. This is a tragic isolation. The vastness of the universe is measured not just by distances, but also by the scarcity of life. As far as we know, we are alone in this immense darkness. But here comes the but moment again. Because this cosmic loneliness is the very thing that binds us more tightly together. There is an experience astronauts call the overview effect. When they look at Earth from space, they see our planet without borders, without the lines that separate countries as a single fragile whole. This experience makes them feel how precious Earth is and how interconnected all life on it is. The deep space traveler may not see this view directly. For them, Earth is just a point of light. But that loneliness, that absolute isolation, deepens the meaning of that single point of light even further. Each of us, on that little blue dot, is connected by invisible threads. The loneliness of an astronaut in deep space is actually a reflection of all of our shared destiny. You are part of this connection. You're a member of that small, crowded planet, and when you set out on the next expedition, you carry not just yourself, but the hope and curiosity of everyone on that planet. Our loneliness is the strongest bond that unites us. And this brings us to the third and most personal contrast, the contrast of past and future. Due to time dilation, a traveller moving at a speed close to the speed of light will be younger than the world they left behind upon their return. This is not just a science fiction idea, it is a proven fact of physics. On a journey at 99% of the speed of light, 1 year on the ship corresponds to 7 years on Earth. This means a tragic separation. The home you return to is no longer your home. You are separated from it not just spatially, yes, but temporally. The people you knew may have aged or died. The culture, the language, the technology has transformed into a future that is alien to you. You become a ghost from your own past, a visitor to your own future. This is perhaps a more painful loss than all the navigation problems, because, this time, what you lose is not a coordinate, but your place in time. But the but moment appears once more, because this temporal disconnect also opens a window to humanity's immortality. That traveller does not journey merely as an individual. They are a time capsule of humanity. To the future they arrive in, they carry a piece of the past they left behind, their memories, their knowledge, and perhaps their wisdom. They are living proof of the continuity of our species. We are temporary beings, drifting in the river of time, but that traveller steps out of that river for a moment and rejoins it at a different point. This redefines humanity's relationship with time itself. You are part of this time journey. You carry the legacy of the generations that came before you, and you pass something on to those who will come after. Each of us, in our own small lives, is a bridge between the past and the future. The deep space traveller merely experiences this bridge in its most extreme, most dramatic form. They are the greatest symbol of this temporal bond we all carry within us. So, what have we learned? We are physically insignificant in the face of the universe's vastness, but we are meaningful through our ability to understand it. We are cosmically lonely, but this loneliness connects us to each other, and we are lost in the flow of time. But we're also a bridge between the past and the future. These paradoxes, these contrasts, are our story. But there is still much more to tell. And yes, there is much more to tell. Because these paradoxes shape not only our relationship with the universe, but also our relationship with ourselves and with each other. This philosophical journey takes us to the heart of the most fundamental human experiences: memory, culture, and the sense of belonging. Now, we will peel back these layers too. This brings us to a fourth contrast, the contrast of certainty and uncertainty. On one hand, there is the human mind's quest for certainty. We draw maps, we set coordinates, we divide time into seconds, minutes, hours. The need to control, to understand, and to predict is one of the most fundamental drives of our species. This is why we built NASA's Deep Space Network. This is why we catalogued 2 billion stars with the Gaia telescope. This is why we brought Apollo 13 home with a window and the sun. We seek precision, because precision means safety. Safety means survival. This is a tragic illusion, because no matter how hard we try, the fundamental nature of the universe is built on uncertainty. As the ether experiment showed, there is no absolute reference point. As time dilation proved, there is no absolute now. And as the proper motion of stars revealed, there is no absolute fixed point. Every measurement we make, every calculation carries a small margin of uncertainty. And this uncertainty grows with time and distance. It starts as a snowflake and becomes an avalanche. This is an unbearable truth for a mind that tries to maintain control. But here comes the but moment, because this uncertainty is also the source of creativity and discovery. If everything were known, if everything were certain, what would be left to discover? What would there be to wonder about? Who would have dreamed up a clever idea like pulsar navigation? Who would have drawn a map like Gaia? Uncertainty is what forces us to build better instruments, to think more smartly, to look deeper. It is the engine of science. It is the fuel of progress. You are part of this dance. You too live between small certainties and great uncertainties every day. You make plans, but you know that life does not always follow those plans. And you also know that the greatest moments of growth come in the most unexpected, most uncertain moments. The deep space traveler lives this human experience to its extreme. They try to find their way in the ocean of absolute uncertainty, clinging to the small islands of certainty created by human intellect. And this brings us to perhaps the most poignant contrast, the paradox of homecoming itself, the contrast of memory and reality. Imagine traveling on a generation ship. The journey takes so long that the ones who try to return are not the original passengers, but their grandchildren or great-grandchildren. What does home mean to them? For them, Earth is a place they have never seen, a place they know only through inherited stories and preserved records. Their home is the ship where they were born and raised. This is a tragic loss, because memories passed down through generations change a little with each telling. Culture drifts, language changes. The powerful pull of homecoming that their ancestors felt may become a faint legend for them. The navigation problem remains just as technically difficult, but the emotional weight behind solving it, the urgency, the longing, can fade with time. The home they are trying to return to has moved away from them not only physically, but also culturally and emotionally. But here comes the but moment, once again. Because this separation is also a new beginning. The generation born on that ship creates their own culture, their own history, their own definition of home. They prove that humanity is not just moving from one place to another, but also transforming. They show that home is not just a planet, but also a shared experience, a community, a story. Perhaps when they return, what they find is not less than what they lost, but just different. Perhaps the real journey is not made among the stars, but among the generations. You're part of this cultural heritage. You have inherited stories, traditions, and a worldview from your ancestors, and you, too, blend these with your own experiences and pass them on to the next generation. Each of us is a living memory, and at the same time, we are creating a new reality. The crew of the generation ship is just an isolated and accelerated version of this process. They do what we all do. They honor the past, but they build the future. Where have these philosophical reflections brought us? We have seen that our relationship with the universe is full of paradoxes. We are small in scale but large in meaning. We are lonely but connected. We are stuck in the past but creating the future. We seek certainty but grow in uncertainty. And while searching for the home in our memory, we build a new home on the way. All of this is the story of our species, as reflected in space. But beyond all these thoughts, there is still one unanswered question, a question that touches not only our minds, but also our most basic instincts, our deepest fears and hopes. At the end of this journey, if we ever truly go that far, do we really know what awaits us? But these thoughts take us to another place, a deeper layer, because even if we don't know what awaits us at the end of that journey, we know something about the desire to embark on that journey itself. This desire, this urge to wonder, to explore, and to understand is one of the most defining characteristics of our species. And now, it is time to ask this most internal question. What do we do with this knowledge? Should knowing that returning home is nearly impossible stop us? Or should it push us even further? This brings us to the first and perhaps most fundamental contrast, the contrast of knowledge and action. On one hand, there is the vast body of knowledge we have acquired about the universe. We now know that the solar system is revolving in the Milky Way at a speed of 500,000 miles per hour. We know that our galaxy itself is moving at over 1 million miles per hour, We know that time slows down as we approach the speed of light. We know that there is no such thing as ether, that the universe has no absolute reference point. This is a triumph of generations of scientific effort, curiosity, and genius. We are, as far as we know, the only beings capable of understanding the workings of this universe. This can be a tragic knowledge, because this knowledge also reveals our limitations. We understand the motion of the universe, but we cannot stop it. We know that time bends, but we cannot control it. We understand why navigation is so difficult, but we cannot eliminate that difficulty. Our knowledge is far greater than our ability to act. It is like knowing exactly what the bars of a cage are made of, but not having the strength to bend those bars. This is a sense of cosmic helplessness. But here comes the but moment. Because knowing is the first step of action. Knowing your limits is the prerequisite for pushing those limits. Understanding why navigation is difficult allowed us to develop smarter solutions like pulsar timing. Knowing that the universe is without reference triggered our effort to create maps like Gaia. Our knowledge is not an invitation to inaction, but a call to more creative actions. It tells us what is impossible, thereby firing our imagination about what might be possible. You are part of this dynamic. You know there are many things in your life you cannot control, but this knowledge does not lead you to give up, but to work more intelligently on the things you can control. Understanding is power, and understanding your limits is the greatest power, because only then do you start looking for ways to get around those limits, or to stretch them even a little. This leads us to another deep contrast. The contrast of means and ends. For centuries, we tried to solve the problem of navigating the oceans. Mariners invented better clocks, better maps, better instruments to precisely measure latitude and longitude. Eventually, they developed chronometers that could determine a ship's position in the middle of the ocean with an accuracy of a few miles. This was an incredible technological achievement. What was the purpose? To travel more safely, to discover new lands, to trade. The purpose was always greater than the means. Now, we look at the problem of interstellar navigation, and again, we develop tools, atomic clocks, gyroscopes, star trackers, pulsar detectors. These tools are incomparably more complex and precise than 18th century chronometers. But this tragically shows that the purpose itself has also changed. When crossing oceans, the purpose was to get from one point on Earth to another. But when crossing the stars, what is the purpose? If there is no return, if the place you arrive at is in a completely different time than the place you left, then the journey itself becomes the purpose. The tools become part of the process of understanding what that goal is. Not just for reaching a goal, it is like climbing a mountain. Initially, the goal is to reach the summit, but as you climb, you realize that the view, the struggle, the feeling of overcoming yourself is also a purpose. But here comes the but moment. Because when the journey itself becomes the purpose, it sets us free. If there is no obligation to return to a specific home, then any place can be home. If the purpose is not just to get from point A to point B, then everything encountered along the way, every star, every nebula, becomes a discovery in itself, a purpose in itself. This is the purest form of human curiosity, the desire to know just for the sake of knowing, not for a reward. You are part of this journey. You use tools to achieve certain goals in your life, a diploma, a career, a house. But over time, you realize how the path to those goals has shaped you, what it has taught you. And sometimes, you understand that the journey itself is more valuable than the destination. The deep space traveler is the ultimate explorer of this truth. They have set out to answer not so much the question, where am I? But the question, who am I? And this brings us to a final thought, perhaps the most peaceful one, the contrast of silence and sound. On the Voyager records, we recorded sounds from Earth, the sound of the wind, the songs of whales, a baby's cry, greetings in different languages. We sent these sounds into a universe we thought was silent and empty. This is a tragic act, because the probability of those sounds being heard is almost zero. The records will drift among the stars for tens of thousands, perhaps millions of years. humming a song that no one will hear. It is a message in a bottle thrown into the cosmic ocean, but the chance of that bottle being found is so low that this act seems almost like a desperate scream. But here comes the but moment, because the real audience for those records was not a hypothetical civilization in space. The real audience was us. The act of choosing, recording, and sending those sounds taught us something about ourselves. It forced us to think about what makes us human, what is valuable, what we want to share. Those records were less a message sent to the universe, and more a love letter we wrote to ourselves. In the midst of silence, we found our own voice, and that voice was more meaningful than the loudest supernova in the universe. You are part of this dynamic. In the quiet moments of your own life, you hear your own inner voice, your thoughts, your hopes, your fears. And when you express this voice through art, writing, or speech, you create meaning not just for yourself, but for others too. Each of us is adding our own small note to the great silence of the universe, and from the coming together of these notes, the symphony of humanity is formed. So, where have these deep thoughts brought us? We have seen that our knowledge is an invitation not to inaction, but to creativity. We have understood that our purpose can be the journey itself, rather than a destination. And we have realized that even in the midst of the greatest silence, we can find our own voice. But there is still one more layer, the most personal, the final layer, and this brings us to the most personal, the final layer, because all these grand philosophical questions ultimately converge on a single point. What does this journey mean for us as individuals? The vastness of the universe, the elasticity of time, the limits of knowledge. How do all these things resonate in our own short, precious lives? Now, it is time to turn this cosmic journey inward. This brings us to a final contrast, perhaps the most important one, the contrast of separation and belonging. The journey into deep space is the ultimate separation. You separate from your family, your friends, your species, your planet. As we've seen, this is not just a physical separation. It is a temporal separation due to time dilation. It is a cultural separation due to cultural drift. It is an emotional separation with the loss of the overview effect. This traveler is separated from the rest of humanity in a way that no one has ever experienced before. This is a tragic sacrifice. It is sacrificing the most fundamental thing a person can have, the sense of belonging, for the sake of discovery and knowledge. It is to be a stranger forever, with an experience that the rest of their species can never fully understand. This is the price of learning the universe's greatest secrets. But here comes the but moment, for one last time. Because this ultimate separation also creates the deepest belonging, just as you appreciate your home more when you're away from it. That traveler who moves away from humanity understands what it means to be human better than anyone else. They are an emissary of humanity. They are a representative of our best and bravest selves. Every one of their achievements is an achievement of our species. Every one of their observations is made with the eyes of us all. They may be separated from us, but they are also a part of us, more than ever before, because they are the embodiment of that primal curiosity, that desire to explore that we all carry within us. They are not alone. Because, in their mind and in their heart, they carry all of humanity. You are part of this dynamic. There are moments in your life when you feel lonely or disconnected, but you also know that you belong to a family, a community, a culture, a species. This dilemma is at the center of being human. The deep space traveler lives this dilemma in its purest, most intense form. They are both the loneliest and the most belonging human. And this brings us to the ultimate question, at the heart of this entire journey. Polynesian navigators, thousands of years ago, crossed the Pacific Ocean without written maps or compasses. They found their way across thousands of miles of open water using the rising and setting points of stars, the patterns of ocean swells, the behavior of seabirds. This is one of the most impressive navigational feats in human history. But what was the secret to this success? A stable, repeating, nearby environment. The stars moved in predictable patterns thanks to Earth's constant rotation. The ocean's swells resulted from predictable weather patterns. The birds were always returning to islands that were in the same place. Their genius was their ability to read their environment. This is a tragic comparison, because deep space is the exact opposite of this stable environment. There is no repeating horizon. There are no fixed nearby reference points. There are no seabirds returning to a fixed island. There are only distant points of light constantly changing with your own speed, and an unforgiving silence in every direction. The greatest genius of the ancient mariners, their greatest strength, becomes completely useless in deep space, because the environment no longer offers them anything to hold on to. But here comes the but moment, because this is not our weakness, but our strength. The Polynesian navigators read their environment. We, however, in a place where there is no environment, create a new environment in our own minds. We draw maps, we write equations, we build models. When there are no physical reference points, we invent mental reference points. The Gaia map, pulsar timing, relativistic calculations. All of these are our attempt to create an order in our own minds that the universe does not give us. This is the greatest triumph of human intelligence. It is moving from reading the environment to writing the environment. You do this too. In the chaos of your life, you create your own maps of meaning, your values, your goals, your relationships. All of these are the mental reference points that guide you in an uncertain world. You too are an explorer, the explorer of your own life. Now we know. At the end of this long philosophical journey, we have grasped some truths. We have seen that the difficulty of finding the way home is not just a matter of technology, but also a deep inquiry into the fundamental nature of the universe and our place within it. This journey has shown us that the smallness of our scale does not prevent the greatness of our meaning. It has taught us that our loneliness can be the strongest force that binds us together. We have realized that memory and the future are as flexible as time itself. We have seen how our quest for certainty is balanced by the creativity born from uncertainty, and we have understood that even the deepest separation can give birth to the strongest belonging. This journey is ending. We have come to the end of these deep thoughts, but every end is a new beginning. Now, it is time to bring all that we have learned together and look at the ultimate answer, or perhaps the unanswerability, of this cosmic riddle. And therefore, it is now time to bring all that we have learned together and look at the ultimate answer, or perhaps the unanswerability, of this cosmic riddle. On this long journey, we saw that our home is not a fixed point, but a constantly moving target. We witnessed how every navigation tool that keeps us safe on Earth becomes useless one by one in the void of deep space. We understood how even the light of the stars bends with our own speed, changes colour, and how our most reliable guides turn into illusions. And beyond all this, we grasped that even time itself is relative, that returning home means not just a journey in space, but also a journey in time to a moment we can never return to. We now know that the impossibility of finding the way home in deep space is not just an engineering problem, it is a truth woven into the fundamental fabric of the universe. Because the universe itself possesses nothing that we define as fixed or certain. Everything is in motion relative to everything else. That is why it is not possible for an astronaut to simply turn around and fly home. Because that little blue dot we call home has travelled billions of miles while they were away, has aged and changed along with everyone on it. It is no longer a destination, but a memory, and you are part of this motion. You too, right now, without even realizing it, are traveling through the galaxy at hundreds of thousands of miles per hour. This knowledge should not make you feel small or insignificant. On the contrary, it should show you how miraculous this journey is. We are travelers in this vast, moving universe, on our own small, moving world, searching for meaning and connection, and perhaps the real home is not a planet, but this shared search itself. If this journey has made you think about your place in the universe too, please like this video and subscribe to the channel, because this helps us to make more discoveries with curious minds like yours. Tonight, we learned that the universe does not give us a fixed address, But that does not mean there are no clues about the beginning of everything, because all this motion, all this expansion, originated from a single moment, an incredibly hot and dense beginning. But even that first moment itself holds one of the greatest mysteries we understand. In this journey, we saw how the moving nature of the universe makes returning home impossible. But there is something I didn't tell you. This motion itself hides a much bigger problem than it should. Our universe, in less than a trillionth of a second after the Big Bang, expanded at an unimaginable rate. This is a growth that no known law of physics can explain. We call it cosmic inflation. In our next journey, we will go to this first moment of the universe, and we will discover how that moment determined the fate of everything we see today. Are you ready?